Ivy Mike was not a bomb, it was a building. Creating a true thermonuclear weapon would take years. But the Americans wanted to test the concept. Would hydrogen fusion work? The device they built weighed 62 tons. It was the size of a 3-story building. It could not be transported. It could not be dropped from an airplane. It could not be used as a weapon. But it would show whether the idea worked. At the heart of the device was liquid deuterium, the heavy isotope of hydrogen, fusion fuel. But keeping it in liquid form required temperatures of -250 degrees Celsius. A massive cooling system was constructed, cryogenic pumps, vacuum vessels, infrastructure the size of a factory. All of this for a single moment, 1/1,000,000th of a second. In that moment, humanity's most powerful explosion occurred. This is the story of how scientists built a machine to create the power of the sun on Earth, how an entire island vanished in an instant, and how the thermonuclear age began with a device too large to be a weapon. The idea of a fusion bomb emerged almost immediately after fission was understood. In 1942, before the first atomic bomb was even built, physicists at Los Alamos began discussing the possibility. If you could fuse hydrogen atoms into helium, you could release enormous amounts of energy, far more than fission could ever produce. Edward Teller was obsessed with the concept. While other scientists focused on the fission bomb that would end World War II, Teller pushed for work on what he called the super, the hydrogen bomb, the ultimate weapon. The Manhattan Project leadership was not interested. They had a war to win. The super could wait. But Teller never stopped thinking about it. And when the Soviet Union tested its first atomic bomb in August 1949, the political landscape shifted dramatically. America's nuclear monopoly was over. The Soviets had the bomb. Some argued that the only way to maintain American superiority was to develop something even more powerful. President Truman authorized a crash program to develop the hydrogen bomb in January 1950. The super would become reality. The decision to build the hydrogen bomb split the scientific community. Robert Oppenheimer, who had led the Manhattan Project, opposed it. He had seen what atomic bombs did to Hiroshima and Nagasaki. He had famously quoted the Bhagavad Gita after the Trinity test. "Now I am become death, the destroyer of worlds." Oppenheimer believed that the hydrogen bomb would make nuclear war more likely, not less. The destructive power would be so enormous that no rational military purpose could justify it. It was a weapon of genocide, not strategy. Other scientists agreed. The General Advisory Committee of the Atomic Energy Commission recommended against building the super. They called it a weapon of mass destruction in a category by itself. But Edward Teller and his supporters saw it differently. The Soviets would develop the hydrogen bomb, whether America did or not. Better to have it and not need it than to need it and not have it. Unilateral restraint was naive. The Cold War context mattered. McCarthy was hunting communists. The Korean War was raging. Fear of Soviet expansion was at its peak. In this atmosphere, Oppenheimer's opposition became politically dangerous. He was accused of being a Soviet sympathizer. His security clearance was revoked in 1954. His career was destroyed. Teller won. The super would be built. Building a hydrogen bomb proved far more difficult than anyone anticipated. The principle seemed simple. Fuse hydrogen atoms together to form helium. This is what the sun does. It releases tremendous energy. But the sun has an advantage. Its enormous gravity compresses hydrogen to incredible densities and temperatures. Fusion happens naturally at the sun's core because the pressure is so immense. On Earth, there is no such gravity. To achieve fusion, you need temperatures of about 100 million degrees Celsius. You need to compress the fuel to extraordinary densities, and you need to do this before the device blows itself apart. The only thing hot enough to ignite fusion was an atomic bomb. So the basic concept was clear. Use a fission explosion to create the conditions for fusion. But the details were nightmarishly complex. Early designs simply did not work. The calculations showed that the fusion fuel would disperse before it could ignite. The energy from the fission trigger would scatter in all directions, not concentrate on the fusion material. Teller worked on the problem for years without success. By 1950, many physicists doubted whether a hydrogen bomb was even possible. Then Stanislaw Ulam had an idea. Stanislaw Ulam was a mathematician who had worked on the Manhattan Project. In early 1951, he proposed a radical new approach. Instead of trying to ignite fusion directly with the heat of a fission explosion, use the radiation. When an atomic bomb explodes, it releases enormous amounts of X-rays. These X-rays travel at the speed of light, faster than the expanding fireball. If you could channel these X-rays to compress a separate container of fusion fuel, you might achieve the densities needed for ignition. This was radiation implosion. The X-rays would squeeze the fusion fuel from all directions simultaneously, compressing it to incredible density before the physical blast arrived. Teller immediately recognized the potential. He refined the concept, adding the idea of using a secondary stage containing both fusion fuel and additional fissile material. The fusion reactions would generate neutrons that would cause this material to fission as well, adding even more energy. This design, known as the Teller-Ulam configuration, became the basis for all modern thermonuclear weapons. Its details remain classified to this day, but the basic principle has been public knowledge for decades. With a viable design in hand, the race to build a test device began. The device that would become Ivy Mike was unlike anything ever built. The design called for liquid deuterium as the fusion fuel. Deuterium is a heavy isotope of hydrogen, with 1 proton and 1 neutron in its nucleus. When 2 deuterium atoms fuse, they release energy and form helium-3 or tritium. But there was a problem. Deuterium is a gas at normal temperatures. To use it in the quantities needed, it had to be liquefied. And liquid deuterium boils at -250 degrees Celsius. This meant building a massive cryogenic system. Vacuum-insulated containers to hold the liquid deuterium. Powerful refrigeration units to keep it cold. Pumps and pipes and monitoring systems. The result was a device that weighed 62 tons. It was about 6 meters tall and 2 meters wide. It looked more like an industrial installation than a weapon. The casing was made of steel, with layers of insulation. Inside was the cryogenic dewar containing the liquid deuterium. At one end was the primary, a fission bomb that would provide the trigger. The X-rays from this primary would compress the deuterium, initiating fusion. This monstrosity was called the sausage for its elongated shape. It was transported to Enewetak Atoll in the Pacific, where a special building was constructed on Elugelab Island to house it. The sausage was not a weapon. It was a proof of concept. Could the Teller-Ulam design actually work? Enewetak Atoll is a ring of coral islands in the Marshall Islands in the central Pacific Ocean. The United States had captured it from Japan during World War II and retained control afterward. Its remote location, thousands of miles from any major population center, made it ideal for nuclear testing. The local population, the Marshallese people, were relocated. Their ancestral home became a nuclear proving ground. They would not return for decades, and when they did, they found their islands contaminated with radiation. Operation Ivy. The military constructed elaborate facilities across the atoll. Observation bunkers, instrument stations, communication centers. Hundreds of personnel were involved in preparing for the test. The device itself was installed on Elugelab, a small island at the northern end of the atoll. A special building was constructed to house the sausage and its cryogenic equipment. Technicians worked around the clock to keep the deuterium at the required temperature. Diagnostic instruments were positioned across the atoll and on ships stationed at safe distances. High-speed cameras would capture the explosion. Radiation sensors would measure the output. Everything was designed to extract maximum scientific data from the brief moment of detonation. The test was scheduled for November 1, 1952. At 7:15 in the morning, local time, the countdown reached 0. The primary fission bomb detonated first. In an instant, it generated temperatures of millions of degrees and produced an intense pulse of X-rays. These X-rays, traveling at the speed of light, reached the deuterium fuel before the physical explosion could disperse it. The radiation implosion worked exactly as designed. The deuterium was compressed to incredible density. Fusion ignited. Deuterium atoms slammed together, fusing into helium and releasing neutrons and energy. The temperature soared to hundreds of millions of degrees. The fusion reactions cascaded, releasing more and more energy in a runaway chain reaction. The explosion that resulted was beyond anything humans had ever created. The fireball expanded to nearly 5 kilometers in diameter, vaporizing everything it touched. The coral island of Elugelab simply ceased to exist. Where it had stood, there was now a crater 2 kilometers wide and 50 meters deep. The mushroom cloud rose to an altitude of over 40 kilometers, penetrating the stratosphere. It spread to a diameter of 160 kilometers. It was visible from islands hundreds of miles away. The yield was measured at 10.4 megatons, more than 400 times the power of the Hiroshima bomb. More than all the explosives used in World War II combined. Ivy Mike had worked. The scientists who witnessed Ivy Mike were stunned by its power. They had expected a large explosion. They had calculated the approximate yield. But seeing it was different from knowing it. The scale of destruction was almost incomprehensible. One observer described the fireball as looking like a diseased brain. The colors shifted through the spectrum as different materials vaporized. Orange, red, purple, gray. A vision of apocalypse. The diagnostic data confirmed what they had seen. The Teller-Ulam design worked. Thermonuclear fusion had been achieved. The yield matched predictions closely. But Ivy Mike also revealed the challenges that remained. The device was far too large and complex to be a practical weapon. The cryogenic system alone made deployment impossible. No airplane could carry 62 tons. No missile could lift it. The next step was clear. They needed to develop a deliverable thermonuclear weapon. One that used solid fuel instead of liquid deuterium. One that could be carried by existing bombers. That development would take another 2 years, but the fundamental proof had been achieved. Thermonuclear weapons were possible. The atomic age had given way to the thermonuclear age, and humanity's capacity for destruction had increased by orders of magnitude. The Ivy Mike test, like all nuclear tests in the Pacific, came at a cost borne by people who had no voice in the decision. The Marshallese people had lived on these islands for thousands of years. Their culture, their economy, their identity were tied to the land and the sea. When the Americans arrived, they were told their sacrifice was necessary for the good of mankind. They were relocated to other islands, often without adequate resources or support. Their home became a nuclear testing ground. 43 nuclear weapons would eventually be detonated at Enewetak Atoll, including the largest American test ever conducted. The radiation contaminated the land, the water, the fish. When some Marshallese were allowed to return decades later, they found that certain foods were unsafe to eat. Cancer rates were elevated. Birth defects appeared. The full extent of the damage is still being documented. Studies continue to find new evidence of radiation exposure and its health effects. The Marshallese people have sought compensation and acknowledgement from the United States with limited success. Elugelab Island, where Ivy Mike detonated, is gone forever. In its place is a circular crater, visible from space, a permanent scar on the geography of the Pacific. The island that was erased from the map cannot be restored. Neither can the lives affected by the testing program. The Soviets were not far behind. Soviet physicists had been working on thermonuclear weapons since the late 1940s. They had their own brilliant scientists, including Andrei Sakharov, who would later become a famous dissident and peace activist. In August 1953, just 9 months after Ivy Mike, the Soviet Union tested RDS-6. It was their first thermonuclear device, but there was a crucial difference. RDS-6 used a different design, one that did not require liquid deuterium. It used layers of fissile and fusion material arranged in a configuration called the layer cake. This made it much smaller and lighter than Ivy Mike. The yield was only 400 kilotons, far less than Ivy Mike's 10 megatons. But the Soviet device was deliverable. It could be carried by an aircraft. It was a weapon, not just a laboratory experiment. The Americans had proven that thermonuclear fusion worked. The Soviets had proven that it could be weaponized. The race continued. In 1954, the United States tested Castle Bravo, a deliverable hydrogen bomb using solid lithium deuteride fuel. It yielded 15 megatons, far more than expected, and caused a major radiation incident when fallout contaminated a Japanese fishing vessel. By the end of the 1950s, both superpowers had stockpiles of thermonuclear weapons measured in thousands. The destructive power available to humanity had increased beyond all previous imagination. What is the legacy of Ivy Mike? First, it proved that thermonuclear weapons were possible. The Teller-Ulam design worked. Radiation implosion could compress fusion fuel to ignition. This was a scientific and engineering achievement of the highest order, even as it opened the door to unprecedented destruction. Second, it accelerated the arms race. The successful American test pushed the Soviets to accelerate their own program. Each success by one side spurred the other to match and exceed it. The result was the massive nuclear arsenals that defined the Cold War. Third, it raised profound questions about the limits of human power. Ivy Mike vaporized an island. Later tests would be even larger. The Tsar Bomba, tested by the Soviets in 1961, yielded 50 megatons. These weapons could destroy cities, contaminate continents, alter the global climate. Fourth, it contributed to the eventual push for arms control. The sheer destructive potential of thermonuclear weapons made their unlimited development seem suicidal. The Partial Test Ban Treaty of 1963, which prohibited atmospheric testing, was partly a response to the dangers revealed by tests like Ivy Mike and Castle Bravo. November 1, 1952. A building-sized machine on a tiny Pacific island, a flash brighter than the sun, an island erased from existence. In that moment, humanity crossed a threshold. We had created the power to destroy ourselves completely, the power of the sun harnessed for war. Ivy Mike was not a weapon, it was a warning, a demonstration of what we had become capable of creating. Whether we were capable of controlling it remains an open question. The crater where Elugelab once stood is still there, filled with seawater now, a monument to human ingenuity and human folly. The island is gone. The questions it raised remain.